Uh, you know why at the early stage the LFP is seldom used for the EV. Okay, the reason why. Actually, this is the reason why. If you observe the discharge curve of the LFP battery, you can find that there is a range. There is a range. The battery voltage just drop very little. That means when the SOC is different, but the battery voltage is almost the same. That means the 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 management system is very difficult to identify how much is the SOC for the LFP. So the protection function is not easy to achieve. Okay, so for LFP battery cells, actually the cycle life is long. But if you assemble the LFP cells into modules or into packs, the cycle life actually is very low. Because it is not so easy to manage this kind of battery because it is very difficult to find out the accurate SOC of the battery. Okay, so this is the reason. Okay, so I hope you can remember this. And yeah, here again, you can see the SOC over the loaded voltage. The loaded voltage means when we charge or discharge the battery. So there is current flowing through the battery, and if we measure the battery voltage, that is called loaded voltage. Okay, the loaded voltage is somewhat related to SOC, and this is NMC. The red curve is voltage, and the green curve is SOC. Okay, as SOC is higher, you can see the NMC battery voltage is higher, but for LFP, as SOC is higher, but the voltage is almost the same. So this is a major problem for LFP. But the cycle life for the LFP cell really is very long. For this example, this is charged and discharged with 1C current, but after 2000 cycle, the capacity retention is almost higher than is almost 90%. You see, and for the batteries, if we want to define the end of the battery, sometimes we say if the retention is lower than 80%, we say the battery is end of life. And sometimes some others will say 70% is the end of life. No matter which one, we will not define 0% of the retention is the end of the battery life. Okay. Usually 70 or 80% is the end of the battery life. So for the LFP, you can see the battery life is more than 2000 cycles. And in this chart, if we use a lower depth of discharge like here, like this one, this is 55%, only 55%. This is a curve. Okay, this is a curve. The cycle life is more than 7,000, and if we charge and discharge 1 cycle per day, then for this 55% DOD, it will last for more than 90 years. If 1 cycle per day. Okay, and for the 65%, it's almost 14 years, and the 75 is 13.5 years. For the 85% is 10 years. So no matter which one, the cycle life is very long. Okay, for the LFP batteries. And this is the discharge characteristics under different temperature. For high temperature is fine. Okay, this is high temperature. and this is the lowest temperature. However, even though the temperature is minus 40 degrees, and you can discharge some amount of the battery out of LFP. So the low temperature performance for LFP basically is okay. Here, this is to compare different kinds of batteries. Okay, this is LMO. Okay, this is LMO, and these two are NMC, and this LFP. For LFP, you can see the voltage is very flat. There is a flat region for the voltage curve, and this is LMO, and these are NMC. Okay. If we discuss the abundance of the different elements, okay, in the nowadays batteries, lithium-ion batteries, lithium of course is one of the elements, and manganese and nickel and cobalt are the elements we used for the batteries, and the abundance means the element stored in the earth, okay. 20 ppm means the concentration of the earth. The percentage of earth is lithium, and 0.1, 10% of the earth is manganese. So manganese is almost unlimited. And this is nickel, 80 ppm, and cobalt. And the reserve means the amount of that element we can exploit. We can exploit from the earth. Maybe the abundance is high, but maybe it is very difficult for us to exploit that kind of element. But so the reserve here is more important. For lithium, for manganese, for nickel, cobalt, the reserve is like this. Although you can see the reserve of nickel actually is very high. Okay, it is very high. But for the nowadays batteries, the use of the nickel is also very high. If we take the Tesla Model S as an example, for one car, it will use 10 kilograms of lithium, 8 kilograms of manganese, 68 kilograms of nickel, and 8.5 kilograms of cobalt. So if we use the reserve to divide it by the use of the element in the Tesla Model S, we can find for the lithium, we can build 1,400 million Model S cars. For the nickel, we can only produce 150 million, and for the cobalt, more than 800 million. That is, if we use the elements at the current speed, the nickel will be exhausted first. Okay, so we have to notice this. And then this is the final kind of lithium-ion batteries. This is LTO, the lithium titanate battery. For this kind of battery, the positive plate reaction actually is like others. Here we take the LCO example, and the positive plate can be LMO, and it can be NMC. That's fine. So the major difference of the LTO actually is on the negative plate. Okay, on the negative plate, it uses lithium titanate. Okay, it uses lithium titanate as a negative plate. Actually, more precisely, the LTO uses lithium titanate nanocrystals. That means the microstructure of the lithium titanate. So the anode surface will be increased. For example, here the surface and the anode surface area here will be 100 square meters per gram. Compared to the graphite, it's only 3 square meters per gram. So the area surface, the surface area is much higher for the lithium titanium nanocrystal used in LTO. That means the reaction speed can be increased a lot. And another very important is the negative plate here use this kind of element. For the other lithium-ion batteries, the negative plate is graphite. Okay, for the others, they use graphite. For graphite, there will be SEI layer produced on the negative plate. Okay, and in the next page, I will explain what is SEI layer. And for this SEI layer, it will become a barrier for the lithium ion to migrate in or out of the anode. That is, it increases the impedance for the lithium ion to reach or out of the anode surface. Okay. So basically, SEI is bad for the battery performance. Okay. So we combine these two factors. The first one is the surface area is higher. The second one is layer is no SEI layer. So the LTO, for the LTO, it allows the electrons to enter or leave the anode quickly and make the high charge current possible. This is the most important feature of the LTO. And what is SEI? SEI is solid electrolyte interface, or sometimes it's called solid electrolyte interface. This word is different. Okay. For the SEI layer, in this figure, you can see this is the SEI layer, and this is a graphite. This is a graphite anode or graphite negative plate. At the first few charge or discharge cycles, that is the formation of the batteries, the solvent in the electrolyte will react with the electrode, and they start to decompose. It will start to decompose the graphite, and the decomposition will generate some lithium-based compounds, and the compounds will precipitate on the electrode, and they will form a few nanometers thick SEI layer. The SEI layer actually is not very thick. It's a very thin layer. It's a very thin layer. It's only a few nanometers thick. It's not so thick, okay? But it will form some. It will hinder the passage between the electrolyte and the electrode heavily, and affecting the performance of the battery. So, as I said, the SEI layer actually is bad. It's not good for the performance of the battery, of the lithium-ion batteries. But an effective SEI layer is also important for the long life of the lithium batteries, because the formation of the SEI layer will prevent the further decomposition of the negative plate. Okay, so the SEI layer actually makes the battery more stable, but it also forms the impedance of the ion or electron mobility. Okay, but for LTO, it uses another kind of element as a negative plate, so there is no such kind of problem. Okay, so this is LTO. But for LTO, the disadvantage is the voltage level is lower than the other lithium-ion batteries. So the most important disadvantage is the specific energy for LTO is low. Okay, but the advantages are extremely long lifetime, the rapid charging or discharging, or intense safety, or low temperature performance. They are better than other lithium-ion batteries, but the low specific energy make the LTO less popular than other lithium-ion batteries. And one other factor is LTO battery now is very expensive. Okay, and you can refer to the figures here. Okay, so this is the low temperature discharge performance, and this is the performance for high charge or discharge C rate, and this is the cycle life. If you compare different kinds of batteries in this radar chart, you can see different kinds of batteries, and they are good for some factors, but bad. They are not so good for other kinds of factors. Here is also the comparison between different kinds of batteries, and you see, I explained this a little further. This outer area means the state of art of the factors of all the lithium batteries. Okay, and the inner circles. The inner circle is the specific kind of batteries. For example, this is the LCO. For LCO, the specific energy is good, is high. The specific power is not so high, and the temperature endurance is okay, and the cost is high. Okay, this is LCO battery, and the LCO battery is okay. It fits the applications like smartphones or laptops. And for the EVs, the lithium nickel, the NMC batteries is applied. For the NMC batteries, the cost is high and the specific is very good, and the lifespan is fine. The temperature endurance is very excellent, and the safety is not so good. Okay, and this is another EV. They use NCA batteries. The NCA batteries, yes, the specific energy is good. The temperature endurance is also fine. And this is LFP. Okay, LFP maybe you can be used for the electric buses because the buses have more space to accommodate the LFP battery, because LFP batteries the specific energy is lower. Okay. But the LFP has a good lifespan and a good safety. Okay, and this is LMO. It is good for the power tools. Okay, this is also the comparison between the specific energy of the different kinds of batteries. The lead acid, of course, is the lowest, and the lithium species is the highest. And among the lithium species, the LTO is lowest. Okay. This slide shows the breakdown, one of the breakdown reason of the lithium batteries. Here, this is called dendrite. Okay, this is the dendrite. This is because the lithium will precipitate on the lithium itself. So finally, it will become the dendrite, and the dendrite may be through the separator and to the other side. So there is a micro short circuit within the cell. This is one of the breakdown mode of the lithium batteries, and this is called the dendrite formation. Okay. Here I would like to talk about the shape and the size. The shape of the lithium-ion battery cell is prismatic. The prismatic usually is rectangular, and the case is hard case. And this is pouch. The pouch is only the aluminum foil, so it's soft. And we can find this kind of cylindrical batteries, and the size is numbered as this is 186500 or 266500. The 80 means the diameter. The diameter is 80 millimeter, and the length is 65 millimeter. And the final zero actually means this is a circular type. Okay, it's a cylindrical type. The final zero. Okay. Of course, we can expect for the larger diameter, the capacity is higher. Okay. But now the Tesla Model 3 use different diameters. They use 21,700, but Elon Musk, well, he prefers to call it 2170. Okay, for this cell, the weight is 70 gram. The volume, the capacity is about 17.3 watt hour. Compared to the Model S battery is 18650. The weight is only 75 grams and the capacity is only 10.8 watt hour. Okay. Uh, the the final kinds of battery I want to introduce is the flow battery. Okay, this is flow battery. The flow battery here, in the figure you can see, this is like a electrochemical experiment. There are two tanks. There are two tanks, and there in the middle there is a separator, and in the two different tanks, they have their own chemical reactions. Uh, if one tank, if under one tank there is a reduction reaction, and for the other tank there will be the oxide reaction. So this is also called redox flow battery. Redox means reduction and oxidation. Okay. Um, for this kind of battery, basically the chemical reactions happens within the tanks. However, if the reaction chemicals in the tanks is exhausted, it can be replenished by the reservoir here. Okay, there are two reservoirs, and it can replenish the active chemicals into the tank, into the two tank by the pump. So the energy density, I cannot say energy density. I have to say, for this kind of flow batteries, it can supply a large amount of energy, because if you have a larger reservoir, then you can supply more energy. Okay, but the energy density actually is not so high, because in addition to the tank, it needs the reservoirs, and it also needs the pump and the control circuit. Besides the tanks here, the cells here, the other equipment is called the balance of plant. The balance of plant, or shortly BOP. The BOP takes a lot of weight and the volume for this kind of batteries. So the energy density actually is not so high, but it can supply large amount of energy. So this kind of energy is suitable for the energy storage for the grid, for the electric grid. Because for the electric grid, we don't care too much about the energy density, but we do need a lot of energy for the grid applications. Okay. The cell voltage is only 1.0 to 2.43 volt, and the manufacturers provide a lot of chemistries, including these ones, to produce the flow batteries. The most popular one is vanadium redox flow batteries. The cycle life is very long, more than around 20,000 cycles. It's very long life. However, the energy density, power density is limited. But anyway, it is suitable for the grid level energy storage systems. Okay, here in this chart we can see the yellow one. The yellow one is flow density. Until 2018, the percentage is not so high, but we expect the flow batteries can occupy more percentage on the energy storage system in the future. Okay, and we say the charge of the battery. We use a CCCV charge method. So the charging circuit have to fulfill the function. And for this circuit, I can explain a little for this kind of circuit. This circuit, the battery is lithium batteries. Sometimes the battery is called accumulators, and the battery voltage is 3.6 volt. At first, if we attach the power source onto this circuit, then there will be a 5 to 50 volt here, and the voltage will make this BJT to be saturated. Okay, because the voltage here is zero and the voltage at the emitter is high, so the EV interface will be saturated. So this BJT is saturated. When the BJT is saturated, then at this terminal will become high voltage, and this high voltage will make the BE interface to be high voltage. So this BJT is also saturated. So then the charging source will supply current to the battery. Okay, and then we can observe that if the voltage here is high and this volt and because the current is present on this pace, so there is a voltage difference between this point and this point. This point will be lower than this point, so the EV interface will also be saturated for this BJT. Okay, and the saturation makes the saturation voltage of the EV interface of this BJT is around 0.7 volt. Okay, so the constant voltage appears on this resistor makes the current here to be a constant current. So at first it will supply constant current to this battery. Okay, and then if the battery voltage is high enough, then the TL431 IC here will be activated. Because for this IC, the voltage here is precisely at 2.5 volt, and this is a voltage divider. Okay, this is a voltage divider. So we have a 2.5 volt here, and we will have a fixed voltage here. So if the voltage is high enough, then the voltage will be limited at some voltage level. So it can achieve the CC and the CV charging profile for this circuit. And yes, for the newer circuit, we can have the specific IC to be used for the charging. And this IC itself can sense the charging current via the resistors here. So it can limit the charging current. And there is a Zener diode here. And the Zener diode will limit the charging voltage for the battery. So this circuit can also provide the CCCV charging to the batteries. Okay, and actually the circuit here is a buck type, is a buck converter. It's a power electronics converter. And this is the inside of the IC. Okay, this is the end of today's lecture. It takes a longer time than I expected. So, okay, fine. At the later part of this lecture, actually I accelerated. So I did not provide very detailed description about the final part of this lecture, but you can read them, and if you do have some problems, maybe we can discuss later or next week or something. Okay, anyway, So this is the end of this week, and I will see you next week. And the other next week, I also have to record. I also have to record the lecture because the students of IMBP cannot be present until next week. So we also have to record that. Okay. So see you.